In this video, we're going to do example 7.6.1. The joint density of x and y is given here, and we're asked to calculate the covariance of x and y and the correlation of x and y. So we remember the computational formula. The covariance of x and y is the expected value of x times y minus the expected value of x times the expected value of y. And the correlation of x, y is the covariance of xy divided by the standard deviation of x and the standard deviation of y. And the standard deviation of x, peeling back the layers of the onion here, is the square root of the variance, which is the square root of using its computational formula, e of x squared minus e of x all squared. And so we're going to need the same thing for the standard deviation of y, which means that we need to calculate all of these little pieces. So we are going to calculate e of xy, e of x, e of y, e of x squared, and e of y squared, all of these using Lotus. So we start out, so it doesn't matter which we start with, we might as well go in the order that they're given. So e of x, y. That is going to be the double integral, and now our bounds are given for us right here. So we don't have to do any work to describe the support. So we're going to go from 0 to 1, and from 0 to x squared of xy times the density function times 20 over 7 x plus y, and that order is dy dx. Now, this is just a matter of multiplying through, crunching through the integral, which we have done many times now, and so I'm going to give you a value that I computed off screen to save us a little bit of work, and in fact I'll do that for all of these integrals. So that's 95 over 294. Next, we have e of x. So e of x is going to be the same basic integral, but instead of x times y, we just want x times the density function. And that as well I calculated off screen and got for us 17 over 21. And all of the functions, all of the integrals, I should say, are going to be the same form, but the function that we have, instead of xy, we'll have x, e of y, this will be replaced by a y, e of x squared, this would be replaced by x squared here, and so on and so forth. So I'll just write down the values that I got for the next integrals. So e of y came out to be 555 over 147. E of x squared came out to be 100 over 147, and lastly e of y squared came out to be 25 over 126. Okay, so remembering that each of these is a double integral calculation like the first two that are on your screen. So now we want to calculate the variance, because we're going to need the standard deviation. So let's go with the variance of x, which is e of x squared minus e of x all squared. So e of x squared is sitting here. It's 100 and over 147 minus e of x, and e of x is 17 over 21 but squared. And if you do that calculation, you should end up with 11 over 441. V of y, and so that's e of y squared minus e of y all squared. E of y is 55 over 147. E of y, that was e of y squared, I'm not sure what I said. E of y is, oh no, I took the wrong value. E of y squared is 25 over 126. Let's move this guy over here and put 25 over 126 there, minus 55 over 147 squared, and that comes out to a delightful 2,525 over 43,218, everybody's favorite number. And then we're in the position where we can calculate the covariance and the correlation. So the covariance of x and y is the expected value of x times y minus the expected value of x times the expected value of y. So expected value of xy was the first thing up here, so 95 over 294 minus e of x, which is 17 over 21, times e of y, which is my 55 over 147. And so that calculation ends up by giving us 125 over 6,174. And lastly, the correlation. So rho of x, y, which can also be written as the correlation of x, y. Well, it's the covariance of xy divided by the sigma, right? The standard deviation of x and the standard deviation of y. And those standard deviations are the square roots of the two variances. So we are going to take in our numerator the covariance, so 125 over 6,174 divided by the square root of the variance, 11 over 441, times the square root of the variance of y, 25 over 43218, which is a hideous looking expression, but it comes down to about 0.53. And I calculate that decimal just to check. Remember, we had this property that minus 1 was supposed to be less than or equal to rho and less than or equal to 1, and indeed it is. So calculating these things amounts to calculating all of the expected value pieces using Lotus, which can be rather lengthy. I saved us quite a bit of time by writing down the answers here and then piecing together the appropriate pieces into the appropriate formulas and coming out with the covariance and the correlation as requested.